Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello, and thank you for joining us today. To start off, could you explain the significance of Bayesian optimization in the context of optimizing industrial processes, particularly in relation to advanced manufacturing?
Bayesian optimization is like having a smart friend who helps you find the best way to bake a cake. Imagine you want to make a cake, but you have many ingredients and different ways to bake it. Instead of trying every single option, which would take a long time and could be messy, this smart friend suggests the best combinations based on what worked well before. In the world of advanced manufacturing, particularly in processes like atmospheric plasma spraying, finding the right settings for machines can be very tricky, like baking the perfect cake. There are many factors to consider, and some of them can change over time, like how a cake might bake differently in different ovens. Bayesian optimization helps here by using past knowledge and current measurements to suggest the best settings. It learns from each trial, correcting for problems like wear and tear on the machinery and changes in the materials. This means we can optimize the manufacturing process without needing to run countless expensive tests. So, just like that smart friend helps you bake a delicious cake efficiently, Bayesian optimization helps manufacturers create high-quality products while saving time and money.
That's a great analogy. Now, could you elaborate on how the Gaussian process modeling structure is specifically utilized to predict coating properties in atmospheric plasma spraying processes? What are the advantages of this approach compared to traditional methods?
The Gaussian process modeling structure is like using a magic crystal ball that helps us see how different factors influence the coating properties in atmospheric plasma spraying. To picture it, imagine trying to predict how a plant will grow based on various conditions, like sunlight, water, and soil type. Instead of just guessing, the crystal ball helps us understand the relationships between these conditions and the plant's growth. In atmospheric plasma spraying, there are many factors that affect the coating, such as gas flow rates and the distance of the spraying nozzle. The Gaussian process models take all this information and create a smart system that learns from past experiences. It builds a predictive map that tells us how changes in one factor could influence the coating's quality, like thickness or hardness. One key advantage of using this approach compared to traditional methods is that it allows for a more efficient exploration of possible settings. Traditional methods might require running many time-consuming and expensive trials, like repeatedly baking cakes with different recipes. However, with the Gaussian process model, we can make educated guesses about which combinations of factors will work best, leading to faster and more optimal results without as much trial and error. And moreover, this model adapts in real time based on the measurements taken during the spraying process, further enhancing its accuracy. It's like having a baking assistant who watches the cake as it bakes and suggests adjustments along the way. This combination of speed, efficiency, and adaptability makes the Gaussian process modeling a powerful tool for predicting coating properties in industrial applications.
That's a compelling explanation. Now, can you delve into the custom parallel acquisition procedure mentioned in the study? How does it differ from standard acquisition methods? And what benefits does it provide in optimizing the atmospheric plasma spraying process?
The custom parallel acquisition procedure is like having a team of chefs working together in a kitchen, each trying out different recipes to find the best one for a delicious dish. Instead of just one chef experimenting with one recipe at a time, this method allows multiple chefs to work on different aspects simultaneously, sharing their discoveries to speed up the process. In the context of atmospheric plasma spraying, this means that instead of running experiments one after another, which can be time-consuming and inefficient, the parallel acquisition procedure allows multiple sets of input parameters to be tested at the same time. This approach is tailored to the specific characteristics of the plasma spraying process, making it more effective than standard methods, which might sequentially test each parameter without utilizing the potential of parallel testing. The benefits of this custom approach include a faster search for optimal settings and improved efficiency. By quickly gathering information from different trials, the optimization algorithm can learn more about how various input factors interact and affect the coding quality. This is especially useful when the number of feasible trials is limited, as is often the case in manufacturing processes. Additionally, this procedure can adapt in real time to the measurements taken during the spraying process, similar to how chefs adjust their dishes based on taste tests. This adaptability helps in ensuring that the final product meets quality specifications while also minimizing costs associated with the process. Overall, the custom parallel acquisition procedure enhances the ability to optimize the atmospheric plasma spraying process more effectively and efficiently.
That makes the concept really clear. Could you explain how the algorithm adapts to real-time process measurements and why this adaptability is crucial for improving reproducibility in the coding process?
The algorithm's ability to adapt to real-time process measurements is like a skilled driver adjusting their speed and direction based on the changing conditions of the road. Just as a driver watches for traffic signals, road conditions, and whether to make instant decisions, the algorithm monitors the performance of the atmospheric plasma spraying process as it happens. For instance, while spraying a coating, the algorithm looks at real-time data, such as the measured voltage from the spray gun, which reflects how well the machine is operating. If the voltage indicates a problem, like wear on the machine parts, the algorithm can quickly adjust the spraying parameters to compensate for this issue. This is crucial because it helps to maintain the quality of the coating, ensuring that properties like microhardness and porosity stay within the desired limits. This adaptability is essential for improving reproducibility in the coating process. Reproducibility is like making sure that every cake baked using the same recipe turns out just as delicious as the last one. By continuously adjusting to real-time measurements, the algorithm can anticipate and correct any undesired changes in the coating properties that might occur due to variations in the process or machine performance. In summary, the algorithm's real-time adaptability ensures consistent quality and performance, making the manufacturing process more reliable and efficient while reducing the likelihood of costly mistakes.
That's an excellent analogy. Finally, could you discuss the validation process of the optimization method in both numerical and experimental contexts? What were the key findings from this validation? And how do they establish the method's effectiveness in finding optimal input parameters?
The validation process of the optimization method involved both numerical simulations and real-world experiments, much like testing a new recipe in both a controlled kitchen and a bustling restaurant. In the numerical context, the method was evaluated using simulated data, which allowed researchers to explore how well the optimization algorithm could predict and select the best input parameters without the constraints of real-world limitations. In the experimental context, the method was applied to actual atmospheric plasma spraying processes. During this phase, the performance of the optimization method was monitored to see how well it could handle the complexities of real-world manufacturing, such as variations in machine performance and material properties. Key findings from this validation showed that the optimization method was effective in identifying optimal input parameters that produced high-quality coatings. The inclusion of real-time data, like the gun's measured voltage, played a crucial role in correcting for wear and changes during the spraying process. This adaptability enhanced the reproducibility of the results, ensuring that each coating met the desired specifications. The results also indicated that the carefully designed Bayesian optimization methods were powerful and efficient, especially in environments where the number of trials is limited due to the expensive and lengthy nature of the evaluations. The combination of numerical and experimental validation established the effectiveness of the method, demonstrating that it could consistently achieve the desired outcomes while minimizing process costs. In summary, the validation process confirmed that the optimization method is reliable and capable of adapting to real-world challenges, making it a valuable tool for improving the atmospheric plasma spraying process.
Thank you for such an insightful discussion. To wrap things up, could you highlight the broader implications of this research for the field of advanced manufacturing? How might these findings influence future practices or technologies in the industry?
The broader implications of this research for advanced manufacturing are significant and could lead to transformative changes in how industries approach process optimization. By utilizing Bayesian optimization and Gaussian process models, manufacturers can greatly enhance their ability to select and maintain optimal input parameters for various processes, such as atmospheric plasma spraying. One key influence of these findings is the potential for more efficient and effective automation in manufacturing. The ability to find optimal settings with fewer experiments means that companies can save time and resources, which is crucial in a competitive market. This efficiency can also enable manufacturers to quickly adapt to changes in material properties or production requirements, fostering greater flexibility in their operations. Furthermore, the integration of real-time measurements into the optimization process allows for continuous improvement and adjustment. This adaptability not only leads to higher quality products, but also minimizes waste and reduces costs associated with rework or material loss. It encourages a culture of data-driven decision-making, where insights gained from real-time data can directly influence production processes. Additionally, as this approach demonstrates success in optimizing complex processes with numerous variables, it sets a precedent for future research and development in other manufacturing domains. The methodology could inspire innovations in machine learning applications within manufacturing, leading to smarter systems that learn and adapt over time. In summary, this research represents a step forward in advancing manufacturing practices. By leveraging advanced optimization techniques, industries can achieve higher quality, reduced costs, and increased efficiency, paving the way for future technologies and practices that further enhance productivity and sustainability in manufacturing.
Thank you all for attending today's discussion. We've delved into the transformative power of Bayesian optimization with Gaussian process modeling, particularly in the context of industrial processes like atmospheric plasma spraying. At the heart of this technique lies its ability to optimize settings efficiently, adapt to process data in real time, and enhance reproducibility through numerical simulations and experiments. We've witnessed its effectiveness in identifying optimal parameters and delivering high-quality coding. Beyond this specific application, the implications for advanced manufacturing are profound. We move towards increased automation, lower costs, enhanced product quality, and data-driven decision-making. This approach paves the way for smarter systems that elevate productivity and sustainability. Our discussion today is a testament to the importance of ongoing research and innovation in manufacturing optimization. Let's continue to explore the potential of these techniques, unlocking new possibilities for advanced manufacturing and shaping the future of our industries.